Hi guys, let's solve the problem container with most water. So we are given an array height of length n. So this is the array height of length n. There are n vertical lines drawn that two endpoints of the ith line. So let's say the ith line is this 0, 1, 2, and the 2 points are I comma 0. So I is basically 6 comma it's 2 comma 0, so that would be this point. And then the second point is I comma height of I, so that would be 2 comma whatever the number is here, which is 2 comma 6. So this is the wall, and basically you have to find two lines that together with the x-axis form a container such that the container contains the most water. So we have to find the container that contains the most water between these two lines. X-axis would be the horizontal axis on the bottom, and the this line would be basically limited by the smallest height of the wall here. So between these two, it would be this wall height. If we were to take it between this one and this one, it would be restricted to the smaller of the two. So how do we go about solving it? Uh, we basically have to find the area of this thing, and it looks like a three-dimensional thing because they introduced the word water, but they have not given the depth parameter, so it is in fact a two-dimensional problem. And how do we do it? So basically we have two parameters. We've got this length to work with and we've got this height to work with. So we can say what's the area between these two? Well, the area between these two is the interval, which is 1. 1 is the interval between this and this. So 1, and then we multiply it by what? We multiply it by the l- least of the heights amongst these two. Because if we were to fill this area, it would start overflowing after it reaches a height of 1. So it would be 1 cross 8. Then we can go, so that would be 1. Then we can go on further. We can do 1 cross, so here there are two intervals here, which can be seen here. So it would be 2 length, and the height would still be 1. So the maximum area would be 2 in this case, and we can go on further to the end of the array, calculate everything, and then we can change our start point to this 8 here. So this is the second index, and if we were to, for example, take the area between 8 and 6, what would that be? That would be, the interval would be 1 here between them, and the least height is 6, so it would be a volume of 6 here. But as you can see, basically what's going on here is we are going n times here, n minus 1 times here, n minus 2 times here, and this will go on for n times. So it's going to be an O n square solution. It's basically a double for loop, an outer loop and an inner loop. So the question is, can we do better? Now, whenever we have to maximize or minimize something and we see a double loop going on as a crude solution, we can always think of a two-pointer solution, because a two-pointer solution will also give us the full range of all the options, and we can have a max or min going on along with that, and that can capture uh, uh, the entire scheme of things here. So what would a two-pointer solution look like? We'll start here with the left pointer on the 0th index. So that would be that, and the rightmost index would be here on 7. So what would be the length? The length would be basically the number of intervals, and the number of intervals would always be minus 1. All the elements minus 1. Why is that? Because, for example, if you were to just pick these two elements, 1 and 8, there are two elements, but there's only one interval. So we can get the number of intervals by saying length of height minus 1. And what would be the height? The height would be the minimum of the left or the right, because that's what it would be restricted to. So if we were to fill water between this one and this one alone, then it would overflow once it reaches beyond this. All right, so we got our height, and we can have a max height function variable that basically pulls the max height from this height that's being calculated. So we can now we have to move. Now, how would we move? Would we move from here to here or from here to here? Well, we'll move from here to here because we have to maximize the volume. So if we move from here to here, that would be a reduction, because in this particular case it will not be a reduction, because the bottleneck was this and not this, and this height is still greater than this height here, so it would remain constant, but we have to try every opportunity to maximize the height. So that means we should move away from the lowest one. So in this case, the lowest one was this, so we'll go on in this one, and you see the heights increase. So that's what we'll do. So let's code this up. So we initiate the pointers left and right, and let's just initiate our max height result as 0. And we'll say for the two-pointer solution, how do we start? The loop would be while L is, so while the left pointer is less than right pointer. We've done that quite many times already, so we should be aware by now. And what is the rest? Well, result should be the maximum of what it already is. This is a very common design practice whenever we have a global variable and then we've got a local variable. Well, the local variable we can either calculate as a separate variable or just put the formula here, but then we have to be sure that we give the global variable a chance to update. So here, what is it? Well, it is r minus l. So that is the number of intervals. And see, here we are not doing plus one. So if we were to, generally we do r minus l plus one, but what that gives is the number of elements itself. But here we are not interested in the number of elements, we are interested in the number of intervals, so which is one less the number of elements. So that's why we'll keep it as r minus l. And then cross what? So cross, we have to do the minimum of uh, height of either l or height of r, because these are the two pointers l and r that we were on, so we have to take the corresponding heights here. So let's say initially res is 0. In the first instance that will calculate, let's see how many intervals are there. 1 2 3 4 5 6 7 8 9. So 9 minus 1, 8 intervals, and it's restricted by one height of 1. So this formula will give us 8 cross 1, which is 8. So res is maximum of 0 or 8, so res will become 8. Well, okay, now we'll go on here. So now we'll see which one of them is the smaller one. So if height of L is less than height of R, then we increase the left pointer. Otherwise, and we don't have to mention the other case as this is greater than, meaning height of L is greater than or equal to height of R. We can just say else R minus equals to 1, because this will capture all the other cases. All right, and then we just return res. So what's going on here? After the first iteration, res became 8, but then we increased our L pointer because L was the smaller one, so we increased it. So the number of intervals dropped to 7. But here the height, what is the minimum height between this and this? Well, it is 7. So 7 cross 7 is 49, which is what we get after the second iteration. So res becomes 49, and then the loop continues to go on. So after the second iteration, left is at 8, right is at 7. So right is the smaller one, so right will change, so it will become 3. So then our intervals are 6, and it would be 6 cross 3 24. So essentially we'll go on, but basically we'll never get to a value over 49, which is what they've painted here. So this is the solution. Let's give it a run, and it passes with flying colors. All right, see you in the next one.